Thank you to the organizers for inviting me to this nice PQC summit. I'm happy to be here. And as promised, I will present FuLeeca, but the real title of this talk is The Rise and Fall of FuLeeca. So if you want to summarize FuLeeca very shortly, it is a hash and sign scheme that is based on the Lie metric. It's using quasi-cyclic codes and a sign matching. And unfortunately, it is vulnerable to lattice-based attacks. If you want to know more details, I first need to show you what is the Lie metric, why are we using it, and what is this sign matching. Then I can describe the scheme and especially the rise of FuLeeca, because it has amazing small sizes, public key and signature. And then, unfortunately, we come to the fall. And here I have to put a disclaimer, because this is a lattice-based attack, and I am not a lattice-based expert. I will try my best to explain the idea, but we do have experts in the audience. So first of all, if I say something wrong, please correct me. But also maybe I can give all the questions on the attack to Vessel. Okay. Let's start with something that I know, the Lie metric. So the Lie metric is actually one of the oldest metrics that we have in coding theory. It was introduced in '58 by Lie to cope with phase modulation in channels. It's defined over integer residue rings, so you have some z modulo m, and if you represent your element between 0 and m minus 1, then the Lie weight of that element is just given by the minimum of x and m minus x. So most people like to represent it with this circle. This is f7, and then the Lie weight would be the shortest path that you need through this circle to reach 0. For example, 2 and 5 have Lie weight 2, and 3 and 4 have Lie weight 3. Okay. What you can also do is consider a more balanced representation, so between minus m half and m half, because then all the Lie weight does is take the absolute value. Okay. Now, as a first choice for FuLeeca, we don't choose any integer residue ring, but we choose our modulo m to be an odd prime. This way, we can make use of easy arithmetics over prime fields. So now I can also speak about vectors instead of tuples. If you consider a vector, then the Lie weight is defined additively. You just sum up the Lie weight of all its entries. This induces you a distance. And if you want to look at the minimum distance of a code, it's defined in the usual way. You take the minimum Lie weight of all your non-zero code words. Great. So somewhere in the slides, I'm surely using this capital M. That just means the maximal Lie weight that we can have in our finite field, which is p minus 1/2. Okay. What is also very easy to see is that the minimum Lie distance of a code is always at least the minimum Hamming distance of the code, right? And that is the main reason why we introduced the Lie metric to code-based crypto like 5 years ago. Random codes can correct more Lie metric errors than they can correct Hamming metric errors. And even better than that, the generic decoders in the Lie metric have a larger cost than in the Hamming metric. So this is very promising. You can have smaller key sizes for the same security level. For signature schemes, we also have a different reason. Hash and sign schemes usually suffer from quite large public key sizes. There are some cute ideas on how you could reduce these key sizes. For example, use low-density generators and quasi-cyclic structure would reduce a lot. Unfortunately, this idea is vulnerable to statistical attacks. I tried to show this with this small picture. If your signature is a linear combination of your secret generators, which have low support, then it will leak something about their support, right? But if we change this to low Lie density generators, we usually have huge Hamming weight, so these attacks can not be applied, but it also seems more difficult from this linear combination of our low Lie vectors to recover which ones we used. Or so is the hope. We need a few more facts about the Lie metric to do some code-based crypto. First of all, we do have a Gilbert-Varshamov bound, and we do know that random codes attain them with high probability. That is great. We know what kind of minimum Lie distance we should expect. We also know that the syndrome decoding problem in the Lie metric is still NP-hard. And we know how vectors of a fixed Lie weight usually look like from this typical set. So that's great things for doing some crypto. Now, as a last ingredient for FuLeeca, I need this new function, the sign matching. If we are considering this balanced representation of our finite field, then I can give my elements a sign in the usual way. Anything below 0 has sign -1, anything above 0 has sign 1, and 0 has sign 0. I also give you a small example. For example, in F7, 5 in the balanced representation would be -2, has sign -1. Okay. If I have two vectors, we can also count how many matches we have between those two vectors, ignoring the 0 entries. And now an important question is, how likely is it that if we have a fixed vector x, if somebody picks at random a y with entries plus -1, that they match at a certain number? And this is just given by the binomial distribution. And then we can define with this the LMP, so logarithmic matching probability, which is -log2 of that probability. This means nothing else than when an attacker tries to find for our fixed x some y, which has LMP equal to lambda, it has a cost of 2 to the lambda. That's all it is. Okay, now we have everything we need for FuLeeca. So similar to other hash and sign schemes, we do have a secret code that we hide, and we publish a scrambled version. As a difference to other hash and sign schemes, we are not using the usual connection between signature and message. For example, CFS uses that the hash of the message is the syndrome of a low-weight vector. We're doing something new. We represent the hash of the message as a vector with entries plus -1, and we want that our signature, which is a code word, has a lot of signs matching with it. Okay, how are we going to do this? Key generation. We want to have a quasi-cyclic code, so we're going to choose some vectors A and P, construct the matrices A and P by taking the cyclic shifts. Then our public generator matrix will be the systematic form of this, and because it's quasi-cyclic, it's enough to take one row of T. Important question, how are we going to sample these secret generators? So our choice was to make this quasi-cyclic code look as random as possible for a quasi-cyclic code. So we put the weight of our secret generators on the GV bound. That's what you would expect from a random code. And we can sample our A and B from the typical set, putting each one at weight d12. There is a hidden detail. We cannot simply take it from the distribution. We need to add some fancy rounding function in order to get close to the actual target weight. There is another hidden detail. If we would simply take A from that, it would be balanced around 0, and you would never get an invertible matrix, so we do a random sign swapping, and then it works. But these facts are not so important, so they're hidden. For the signature generation, I'm also going to hide a lot of details. Iterative algorithm is in red because that makes signing a bit slow. So the idea of the signature generation is to go through all the rows of G and either add or subtract the rows until you have a code word that has two conditions. The leeway should be small, not too small, and it should have a lot of matches with the hash of the message. And then, because we have our public generator matrix in systematic form, it's enough to publish this vector y instead of the whole code word, because then the verifier can make this backwards, recover the code word, and check the two conditions. Very simple. Let's get to the rise of FuLeeca. And so I have to explain some parameter choices that we did. For example, why is this P that we chose so high? So as I said, we put the weight of the key on the GV bound. And then if we try to plot, not very nicely, the cost of the generic decoders, it tells us in order to reach a certain security level, we cannot choose the weight of our signature larger than some point, right? Now, P is this high because we need the difference between the weight of the signature and the weight of the key to be big, such that the iterative algorithm makes many rounds and you can get enough sign matches. If I was able to just add or subtract 1 or 2 rows, I would never get enough sign matches. Okay. Even with such a large P, we get very nice sizes for public key and signature. For example, level 1 in total size is 2.4 kilobytes, which is really good. Also, verifying is very fast. We can also compare ourselves to the other code-based crypto systems in the round 1. I always took the short variant. To show you FuLeeca is down here. Timings is, we are a bit slow in signing, which is often with hash and sign schemes, but we're very fast in verifying. And now that you're all convinced that this is a promising and great idea, we come to the sad news. And again, the disclaimer, I'm not a lattice-based expert. So in lattice-based crypto, they use this Euclidean metric, right, which is the L2 norm. The Lie metric is just the L1 norm, okay? So very similar, and we also know that the L2 norm can be reduced to any LP norm. This means you can use Lie metric algorithms to solve problems in the Euclidean metric, but the other way around. Use Euclidean algorithms to solve problems in the Lie metric is not known and is assumed hard. But then you can ask me, why were we attacked by lattice-based algorithms? Because for our instances, you can go the other way as well. So which choices did we do which allowed this? First of all, there is no modular reduction. Our signature V is a code word, so we have some information vector X multiplied to our generator matrix. And this is actually done modulo P. But because we chose our vector X to have such small entries, you can ignore the mod P. And seeing some signatures, you directly get the integer lattice, LG. We could put larger values in X in order to avoid this, but then we also get larger weights in the signatures, which enable forgery attacks. So bad idea. Second of all, the quasi-cyclic structure. Because they already see the integer lattice LG, now they can also work just with 1/2, the LA, which is now a circulant lattice, which might enable sub-exponential costs, so very scary. Can we avoid this? Well, we can put not a quasi-cyclic structure, but then we get public keys, which are huge. And I think this one is the biggest problem that we first need to solve if we ever want to use the Lie metric in crypto and consider it code-based and not lattice-based. So when they apply Euclidean algorithms, they find the short Euclidean vectors. And to my intuition, they should not give you your small Lie weight vectors. No, they are, but they are exponentially many, hopefully, and then only a few of them are also those that are of small Lie weight. For our instances, this is not the situation. They do get that the shortest Euclidean vectors are the ones of small Lie weight. Right, so this attack is by Felicitas Herman and Wessel van Werden. Yeah, so we would be very happy if somebody wants to pick up this topic and repair the Lie metric, because we hope we were able to show its potential. I especially want to thank my FuLeeca team. 2 of them are here, Patrick and Sebastian. If you want to have to look at the slides or at the specification, because now you got interested in FuLeeca, you can scan either one of these QR codes. And thank you for your attention.